Optimal health for high performers. This is the Health Upgrade Podcast with Dr. Nawaz Habib.
Welcome to a new episode of the Health Upgrade Podcast. In today's episode, we're really excited to have a really special guest. It's Dr. Czuras Journey. Now, Dr. Czuras Journey is a molecular immunologist who has been studying vagus nerve stimulation for the past 20 years. He has made seminal discoveries in neural control of bleeding and inflammation, and results of his research have supported the development of two bioelectronic medicine startup companies, one of which is developing a proprietary implantable vagus nerve stimulator to treat rheumatoid arthritis, and a second that is developing a wearable vagus nerve stimulator to control bleeding. Chris has also participated in other early stage companies in bioelectronic medicine, pharmaceuticals, and wearable and off-body diagnostics. He serves as Vice President of Scientific Affairs at the Feinstein Institute for Medical Research, that's Northwell Health in Manhasset, New York, overseeing all aspects of laboratory operations, the annual budget, and construction and renovation projects. He coordinated strategic plan development with the president and board of directors, and represented the research portfolio to senior leadership of Northwell Health. Chris has authored or co-authored over 100 peer-reviewed papers, book chapters, and meeting abstracts, and presented to audiences in science, military, industry, venture capital, and philanthropy. He has been awarded 2 international patents and has an additional 2 patents pending. As I'm sure you can understand, I'm very, very excited for today's episode and for this recording. It was a wonderful conversation, and I'm sure those who are in the scientific community and those who are interested in understanding vagus nerve stimulation and the development and the discovery of the cholinergic anti-inflammatory pathway will absolutely love today's episode. I hope you enjoy it. Here we go.
Great.
Hello, everybody. Welcome back to the Health Upgrade Podcast. I'm very, very excited today. We have a very special guest with us. So I am joined by JP Erico, my co-host for this season, but we are very excited to also have a special guest with us by the name of Dr. Czuras Journey. Wonderful to have you here. We're excited to learn about your journey through the research realm in vagus nerve, cholinergic anti-inflammatory pathway, and all of the amazing eureka moments that kind of popped up throughout your journey. So it's an honor to have you here.
It's my honor to be here. Thank you very much for the invitation. I look forward to this conversation.
So why don't we start off a little bit with your journey? What brought you into this realm, and where was kind of that initial spark of excitement when you started learning about the vagus nerve and getting into the Feinstein Institute?
It was quite by accident. I was a graduate student at Stony Brook University, and I was doing some work in fruit fly genetics. And I had decided that I didn't quite see the career path I had hoped for with the work I was doing at Stony Brook. It's a great program, but I didn't quite see where that was going to take me career-wise. And so I took a leave of absence from Stony Brook. And after going through the initial didactic part of a PhD program, before I jumped into my full dissertation project, I took the leave, and I just, by, I suppose, dumb luck, joined what is now the Feinstein Institute. The Feinstein Institute itself took several turns during my 20 years there, but it's got quite a history to it. But it was truthfully quite by accident. I stumbled in there. I answered a job ad and joined as an editor, part-time. Half the job was as an editor for a journal that they were publishing called Molecular Medicine. The other half of my job was writing grants. And I started my very first grant writing assignment was with Kevin Tracy, who's now the CEO and president of the Feinstein. At the time, he was an active neurosurgeon. And I joined his lab after writing a grant or two with him. I joined his lab full time. And as a busy neurosurgeon, he didn't really have time to be in the lab all day every day. He was either in practice, in surgery, or was out doing a roadshow, giving talks and things. And so I was kind of the day-to-day manager of the lab. helped him run the lab, keep things going. And it was truthfully, even in that very first grant I wrote with him, I saw the career path that I had hoped to get and hoped to be on. And I saw the opportunity to do that there with him. And so that was how I landed there.
It's always one of those fun experiences when it just kind of shows up and the universe says, this is the way to go. I always love hearing those amazing stories. JP, did you have a question there?
Well, so I just wanted to ask about the first projects that you were working there. You sort of indicated along the way when we were discussing having you come on the podcast about that first paper that you were involved in editing, and it's one of my all-time favorites. Definitely one of those eureka moments in science where somebody discovers something unexpected. And so tell us about your very first paper that you were asked to edit when you were there.
Yeah, I had the good fortune of working with Ludmila Borovikova, who was the first author of the first paper that came out of the Tracy lab that talked about vagus nerve stimulation, controlling inflammation. If I back that story up a little bit, some of which is prior to my actually joining the lab, so I like to ascribe to, I think it was Albert Einstein's notion that, it's not the eureka moments in science that are the indicators that something big is happening. It's the, that's weird kind of moment, right? And that's exactly how we landed on the vagus nerve story. We were actually working on, the Tracy lab had always been interested in finding new ways to control inflammation, and came at that question or that mission by looking for endogenous pathways that control inflammation, figuring that, well, if there are natural mechanisms in place, if we can make them work better, we're likely to have a better outcome. So we were actually working on an experimental small molecule that was designed to inhibit cytokine synthesis in macrophages. And what it turned out, what happened was when you're working in vitro, you can kind of calculate or predict what kind of dose you might need once you put the compound in vivo into an animal. And it turned out that compound worked at doses 100,000-fold lower than was predicted by what we were doing in vitro. And that was a very much that's a weird observation kind of moment. Because if anything, when you put an experimental compound in vivo, you wind up having to increase the dose, not decrease it. And so we began rationalizing our way through, trying to explain how that might happen. And the only thing that made any kind of sense is that there was some sort of a second messenger. And in part because Kevin was a neurosurgeon, so he's normally thinking nervous system anyway, and in part because of some of the technical details of the experiments we were doing, we got on the notion that this drug or this compound was actually entering the brain and activating a neural second messenger. And rationally, that's got to be autonomic nervous system, not voluntary nervous system. And if you're in the autonomics, it's either sympathetic or parasympathetic. And honestly, again, as the neurosurgeon to Kevin, the easiest thing to do was eliminate the parasympathetic by cutting the vagus and see what happens. And sure enough, we lost the effect of the drug when we cut the vagus. And that was what really opened up the door to say, hey, you know what, wait a minute. The brain is controlling the immune system through the vagus nerve. And now the vagus nerve gives us all kinds of targets. So we looked at how we might modulate the vagus nerve from inside the brain with a compound, how we might mimic acetylcholine, the neurotransmitter of the vagus nerve, use that as an experimental therapeutic. And then the third was actual manipulation of the vagus nerve itself, which led to stimulation. So that was kind of the backstory of how Ludmila even got to doing that first set of experiments that were published in Nature.
Yeah, that's one of the great moments for me when I had the opportunity to read that paper. And embarrassingly, it was after we did some of our own work. We were not trying to do the same thing. We were trying to do something completely different. For our group, it was looking at anaphylaxis, and there had been a paper that had been published, which in some ways sort of went the opposite direction than ultimately we found the mechanism to be. The paper was out of an old journal from Russia where they had taken dogs and sensitized the dogs to hen albumin. And so when they exposed the dogs that had been sensitized to egg white, the dogs had an anaphylactic reaction. And if it was a significant enough challenge, the dogs would die. And what they did was they cut the vagus nerve in the animals. And you would think that by cutting the vagus nerve, that would sort of exacerbate the problem, because now the allergen's activating the system even without any brakes being applied. But they actually saw the exact opposite. The animals that had the vagus nerve cut were able to survive. And we've talked about this on earlier podcasts, but the thought process that I was led to think about was when another neurosurgeon, believe it or not, it's a great field for coming up with good ideas. The neurosurgeon said, anytime anybody's ever cut a nerve and gained a clinical benefit, well, you can stimulate the nerve and get the same benefit. So I took that idea and put it together with what the Russian paper was talking about and said, hey, let's stimulate the vagus nerve and see whether or not we can stop an anaphylactic reaction. And in 2006, which is, 6 years after the work that they had done, that you were doing actually at the Feinstein, we did the work at Columbia and showed that we could take an animal that was lethally exposed to an allergen, would be able to survive it. And we found some really interesting facts about how long, what the duration of the benefit was, and that even just a very acute stimulation would provide sort of protective benefits for, well beyond an hour. You could continuously re-expose the animal to the allergen and was no problem in keeping the animal alive. They would have something of a reaction, but it wouldn't be anywhere near as detrimental as the lethal reactions that the other animals were getting. So I love that paper. I love the fact that it explained what it was that we were seeing. We sort of came at it from a different direction than trying to understand the science. It was more, how can we make something that would be able to leverage this observation? So, but it was a great paper. Were there some eureka moments? We had some eureka moments along the way that I don't think I've shared yet. So I'll do that right now. We had our very first I say prototype device, but it wasn't even ours that we created. It was a device that was used for nerve conduction velocity testing. It's about an $80,000 machine. It's got a head on it that's about a foot wide, and it runs at very high energies. It was about an $80,000 machine. We got it out of Scandinavia, and we were sort of playing with it, seeing whether or not we could run our own signal through it. But we had a person who worked in one of the other companies that we were working with who had really bad asthma, and he hated using his albuterol or Primatene Mist or anything like that. Hated the way it made him feel. And so we were already working with animals, and we knew that we could stop an anaphylactic reaction, and the anesthesiologists were telling us about the benefits it might have in asthma. And so he said, I'd love to try it if it's ready, because I really don't want to take the albuterol. And so we had an anesthesiologist there with us, and she said, sure, let's give it a shot. And so he put this gigantic thing up to his neck, and he's moving it around, and the signal's coming through his skin into his neck. And he's like, wow, I can feel it in my ear. I can feel it in my jaw. I can feel it in my teeth. And then he said, wow, it's gone. Wow. It's gone. And he starts taking deep breaths. He's like, I can usually trigger an asthma attack, but I can't trigger it. Like, it's gone. So it was that moment of like, holy crap, this is going to work. So, and I had the opportunity to talk with one of the founders of Cyberonics, obviously the granddaddy of vagus nerve stimulation in humans, and sort of understanding how they developed their implant along the way. And they had a moment that was not in humans, but it was in dogs, where they had been using strychnine poisoned dogs to test for anti-seizure benefits of vagus nerve stimulation, because a lethal dose of strychnine will cause an animal to go through a period of continuously seizing. And what he said was that they had this dog that was seizing, and they put the vagus nerve stimulator, wrapped it around the vagus nerve, and started the signal, and the seizure stopped. And I said, wow, that must have been just a miraculous moment. And then he said, and we turned it off and the seizure came back in about 5 minutes. And so I said, oh, that's really interesting. Is that where the every 5-minute stimulation parameter comes from? And he said, yes. And I said, boy, that's really interesting because that's not really epilepsy. That's not naturally occurring epilepsy. Did you dose range it when you got to naturally occurring epilepsy? And he said, no, that nobody ever asked them to. And I thought to myself, oh, that's interesting, but you never get away with that with a drug. And yet all the evidence we've seen is that that's not a treatment paradigm or protocol that's necessary. So do you have any insights into that and any experiences like those sort of eureka moments that you were a part of?
Yeah, I mean, there definitely were. And, there's a number I can point at. I told the story about the drug leaking into the brain and turning on the nerve. And, that was one of those contemplative moments. But there were others that, kind of as both of the ones that you described are, in some ways, they're premeditated. Like when we did that first experiment with the drug, there was absolutely no reason for us to think that had anything to do with the autonomic nervous system. And so that's why that was one of those, that's weird kind of moments as opposed to a eureka moment. Later there definitely were eureka moments when we had more data, we had a hypothesis, and we did some bizarre experiment that all of a sudden it's exactly kind of what we expected, or it was directly supporting the hypothesis that we had generated going in. And those were things like, so we talked in the beginning about Ludmila Borovakova's paper doing the electrical stimulation. I think the other, in some ways, a little bit more unsung heroes in the story is Hong Wang, who had done the genetic manipulations to demonstrate that the acetylcholine receptor and the alpha-7 subunit is responsible for this pathway. Hong, she did, it was just an amazing amount of genetics and manipulations that she had done, back when the tools weren't as robust as they are now, to prove that receptor and that one specific subunit was so remarkable. She too published that in Nature, I think in 2003, if I'm not mistaken. And that was definitely one of the moments that, identifying that acetylcholine receptor on macrophages, and it, that was one of those moments. There's a couple. Valentin Pavlov had done work where he put a galantamine into the brains of I don't remember if it was mice or rats now, and he showed that he turned on the pathway from the brain. That was another moment that was just remarkable. And then Mauricio Spallina had done some experiments that he wound up publishing in Science that mapped this pathway down to the spleen and to a T cell. And that was another moment in time when it was just like, holy cow, because when Mauricio started his project, yes, it was clear that acetylcholine and the cholinergic receptor on the macrophage explained what was happening in the immune cell. But that's when the story began about, well, wait a minute, how does the vagus nerve get to the spleen? Because there's not a known anatomical connection directly to the spleen. So how is the vagus nerve releasing acetylcholine to circulating macrophages? And that's when Mauricio got in there and rolled up his sleeves, and he found out that no, it's right. The vagus nerve doesn't go there. It's a splenic nerve driving noradrenaline, and that this T cell is picking up that noradrenergic signal, converting it to an acetylcholine signal, and that's what's hitting the macrophages. And so those are, I think, some of the biggest moments in this story. And there's tons of others. As we were doing work in, we were doing work in humans. We were looking at the effects, looking at even in arthritis back then. And, there were just a whole series of things happening in and around that. But those were some of the key landmark moments that we can look back on that really kind of stitched this whole story together.
Yeah, that part about the T cells. That's why I almost stole your thunder there by bringing it up. T cells are that role that the nascent chat cells has is remarkable. That beta 2 receptor and the ability to then release acetylcholine. It triggered in my mind back when I first read those papers that those cells were acting almost like interneurons. in that they were converting the noradrenergic signal into the cholinergic signal. And the idea being that how does the immune system interact with the central nervous system? And one of the themes that Dr. Habib and I have been talking about on this podcast throughout this series is the fact that the brain and the immune system, or the central nervous system and the immune system, really aren't that different. In fact, I view we've talked about the fact that I view the central nervous system as the third arm of the immune system, that the central nervous system is the proactive immune system. You have an innate immune system that sort of is our reptilian version of an immune system. Then you have the adaptive immune system, which sort of learns from the mistakes that were made and learns how to avoid it or defeat it when you come in contact with it again. But the nervous system has the ability to prevent us from getting injured, prevent us from getting ourselves in circumstances where there's a high likelihood of a pathogen, getting into our systems, and that together they keep us safe. And that there's, even at the highest levels of evolution with humans and higher primates and other and maybe dolphins, et cetera, there's an emotional ability or ability to sort of foresee the future and avoid injury and damage, and even experience injury and damage from stress, from concern or risk, or understanding of risk in the future. So I think all of that I map in my own mind back to that first recognition that a T cell was acting like a nerve. It was acting in some ways like part of the nervous system, not part of the immune system. So I find that really interesting. You made an interesting point about how the eureka moments don't always happen when you have a theory or a hypothesis that you're trying to test. Sometimes it's just observation of the weird, observation of the unexplainable. And we had a few moments like that as well. One of the great jumps forward for us was the ability to stimulate the vagus nerve non-invasively. So we like to work in humans because that's who we ultimately want to treat. And it's really difficult when you have to do surgery or do some invasive procedure. Not a lot of people, raise their hands and say, yeah, sure, I'll try that. Let's do that right now. But once it's non-invasive, there's an ability to try it sort of, on everybody, or everybody that's interested. And so we had moments like that where people were reporting back just little things that you said to yourself, wow, we weren't expecting that. And all of a sudden it's, why is it opening up these people's sinus path, their sinuses, and people are looking at us like, wow, this is like Afrin, or this is like, a spray up my nose. It just opened up my sinuses. And then people saying, about their headaches going away, and then reading in the literature about people studying it in fibromyalgia and the work that was being done at Cyberonics in depression. There were moments where we actually wondered whether or not it was all snake oil. If it's being used to treat everything, then it's doing nothing. And I stepped back and said, I think that if it's doing this many things, it's got to be doing something very fundamental, very, very fundamental to life itself. And so, one of the questions I have is, how much work was done to sort of map it back and say, how far back does this pathway go? It's not just humans that have it. Obviously, lots of animal models are being created. How far back do you think it goes? I mean, is it invertebrates? Is it reptiles? I mean, where do you think this evolved?
That's a great question. And honestly, I'm not an evolutionary biologist. That's not something I tend to think about all that much. And as a result, I've forgotten some of the details that some people do point at that talk about that. I think certainly, if we're just talking about the immune system, that is, as you pointed out just a minute ago, quite ancient, especially the innate immune system, the dumb part of the immune system, if you will. But when and where neural control of that system evolved, I don't really know. I would think it's pretty early, though. That the roots of the vagus nerve and the autonomic nervous system go back quite far phylogenetically. I don't want to speculate as to kind of when and where that began, but I would say that it's more than likely it is quite ancient. And I think the important part of that, or one important part of that, I mean, obviously knowing where that all came from and understanding it from its roots is really crucial. But I think the other thing that kind of suggests, which is what I like to think about and figure out, in addition to your point, the transcutaneous approaches, which is kind of what I really, that's kind of my main thing. I think the transcutaneous approaches are really the right way to go. But knowing that, or under the assumption that this is a very evolutionarily conserved ancient pathway, really opens up the conversation about, well, ultimately, what does that mean? And so in my mind, what that means is, primarily that the innate immune system, the immune system probably more broadly, and the central nervous system are in this constant contact. And it's information flow to the brain and then motor signals back down to wherever, right? To your point, we can talk about spleen, liver, blah, blah, blah. But that's a very intertwined pathway. And I can say this because I'm an immunologist. Immunology suffered for a long time of a very reductionist approach to science. And there was this notion that the immune system worked in complete autonomy, disconnected from the brain. And we now know that's not true, in part because of the work done at the Feinstein and also in many other labs around the world. And that means that there are all kinds of things happening in the body that the brain knows about and that the brain controls, only a very small fraction of which we're actually conscious of. And now that begins to explain why things like depression and rheumatoid arthritis have all these comorbidities that go along with them that don't necessarily line up with inflammation. It explains why gut dysbiosis may actually have profound health effects that aren't directly related to the microbiome in the gut, but is actually causing misfiring signals to the brain, and then the brain is responding inappropriately. And then I'll end just by saying that the other thing it conjures up is this notion that something like rheumatoid arthritis, while manifesting as an autoimmune disease, may actually originate as a problem in the brain. And all of these things are really, really intertwined as a result of that deep evolutionary conservation of this pathway and the long-term connections between these two systems.
Yeah, one of the things that I've been spending a lot of time recently working and trying to understand better is the role that the innate immune system has in embryology, in gestation, in actually forming the other organs. Some of the work that's just been done within the last 5 to 10 years, and some of it even within the last couple of years, explains how the brain itself is formed and the incredible role that macrophages, embryonic macrophages, which are actually microglial cells, play in the formation of the brain. They're involved in neurogenesis. They're involved in every aspect of the synapse formation, pruning, the oligodendrocytes and the progenitor cells and which way they differentiate, even the vasculature and the formation of the vasculature within the brain, the laying down of white matter tracts. All of that is really controlled by the microglial cells, and the migration of those cells into just the small cluster of neural progenitor cells that are forming, that's going to be the brain. That happens within the first week of after conception, and those cells last for your entire life. And so it's really it's a fascinating way and perspective of looking at the human body and the brain, and actually there's an equivalent process that's happening in the liver with the migration of macrophages, within that first week of gestation into the embryonic liver, and they become Kupffer cells that last with you for life. So there's the incredible role that the innate immune system, it may be that first and most, and as you said, the sort of the dumb one, but it's also the most powerful, because it's doing so many different things. So I think if you look at it from that perspective, maybe it really is true that this is a conserved process that's goes back really to the very beginning of multicellular organisms, that there's some level to which there's a vagus nerve. I think somebody said there's a vagus nerve in a sea sprite. I mean, so that they're pretty primitive animals.
I thought about saying that I think there's data that says that the C. elegans, the flatworm that is such a mainstay in genetic research, I believe they have some rudimentary autonomic nervous system, whether it's the vagus nerve specifically or not, I don't know. But I do believe that it goes that far back. But again, not an evolutionary biologist.
Understood. Neither am I. So let's maybe spend some time. I know that Dr. Habib has a bunch of clinical questions. Would love to dig into some of the work in both rheumatoid arthritis and maybe into the inflammatory bowel disease.
Yeah, you had mentioned gut dysbiosis, and this obviously sparks a functional medicine doctor to be like, hey, let's talk about that. And so you mentioned really interestingly that gut dysbiosis may be the trigger for misfiring within the brain, but the actual function of rheumatoid arthritis as an autoimmune condition, in quotes, may actually be due to some sort of central issue in the nervous system. Let's talk a little bit about some of the findings there.
Yeah, so I think that's more of a logical deduction, perhaps, than hard fact observation that there is that brain dysfunction or central nervous dysfunction can directly cause an autoimmune disease like rheumatoid arthritis. But it flows quite logically, right? If everything that we and others have shown is true, that the brain can control the immune system, and specifically control inflammation, then it's very plausible that a brain condition where those motor signals originate, or where the sensory side ascends to the brain, right? If the brain doesn't receive the signals appropriately, or if it mounts the incorrect motor response, it could be central pathways that are aberrant that then lead to or allow for excessive inflammation and manifestation of things like rheumatoid arthritis and inflammatory bowel disease. It's completely logical. Yeah. How much data of that supporting that actually exists, I'm not sure. Again, I'm more on the immunology side and very much on the basic science side. And so I don't want to claim that I'm in direct contact with all the clinical literature here. But it's certainly quite plausible.
And there's work that's done in more the clinical side of gastroenterology, for example, looking at how stress can trigger an immune response that raises TNF alpha levels and fecal calprotectin levels and things like that. So there's no question that the brain can be triggered into what is more of a sympathetically driven pro-inflammatory condition, and as a result, the body responds by raising inflammation levels. So that work is there on the clinical side. I know of it in the gastroenterology field. I would assume that there's a parallel in the rheumatology field, looking at things like rheumatoid arthritis or psoriatic arthritis or things like that. I would imagine that those are there as well. We also know just observationally that high stress is something that leads to atherosclerosis, and there's clear indication that the sympathetic nervous system plays a role in enhancing the progression of atherosclerosis by motivating and invigorating an immune response. So I think if we look around at various different areas and understanding how stress impacts our lives in a pro-inflammatory direction, and that's all mediated, because there's no physical damage that's being done to us directly. It's through stress and our response to it that I think we can say that the brain clearly has the ability, if it's not functioning properly or not tolerating the environment properly, to trigger a pro-inflammatory response that could end up being pathological.
Yeah, absolutely. In an earlier life, I spent a few years as an auto mechanic, and I tend to think about things from a perspective of a car or a mechanical system. And when we talk about parasympathetic and sympathetic, the sympathetic nervous system is the gas pedal. Go, 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 right? Whereas the parasympathetic is the brake. It slows everything down. It's the fight or flight versus rest and digest story. And if the sympathetic nervous system is in overdrive, all of those downstream consequences are going to manifest. And I personally suspect that there are these can manifest in different ways. I think that's why we see the clinical variability. I think it depends on exactly what neurons and exactly what organs they're feeding or wherever they're terminating, that will drive the manifestation differently in different people. But I think without a doubt, that's exactly what's happening. And that's why applying electrical stimulation to the autonomic nervous system, the vagus nerve in particular, can have such diverse effects, because really what it's doing is putting the brakes on the sympathetic nervous system.
So one of the things that we were talking a little bit about how the innate immune system is involved in brain development and literally the neurodevelopment that happens in gestation, in utero, and early life, which progresses all the way through life, by the way. But that when inflammation, whether it's even in utero or in early childhood, is present and significant inflammation, that can lead to the priming of microglial cells so that they then respond more vigorously for an extended period of time, much the same way we talk about in concussion. Person gets a concussion, how long do they have to stay out of sports? Well, it's probably beyond when they're just having some clinical symptoms, because there's things that are going on with those immune cells in the brain that last for quite a long time. And so what we're maybe dealing with is that there's some early life experiences that may have primed some subset of microglial cells in the brain that, as a result, in the future, those individuals are more susceptible, and that stress will then will have a response in them, or their response to the stress will manifest itself in some specific way. It might be in depression. It might be in an autoimmune disease. It might be in cognitive dysfunction. It might be in metabolic dysfunction. Any one of those things could end up evolving into a disease that is really the result of how the brain and the microenvironment in the brain has been primed to be susceptible to it.
Yeah, there's a fair amount of work going on in that space. Again, it's not a space I know all that well, but one example I know just because of my career path, Betty Diamond's group at the Feinstein is doing some pretty remarkable work in lupus, and looking at what happens when fetuses, these are mice, are exposed to certain things that the mom experiences. And how that predisposes that fetus for lupus later in life. It's really some pretty remarkable things. And speaking of Betty Diamond, the other interesting work that she and Kevin Tracy are doing or have been doing is looking at. There's another. I'm taking this in a totally different direction, so you can stop me if you want.
No, go ahead, by all means.
But the other fascinating part is thinking about, again, how the brain is controlling how we experience our lives and what it means in terms of disease progression. There's a very significant clinical syndrome known as sepsis that I think 250,000 Americans die of every year, but nobody's really heard of it. It's a massive, massive clinical problem. Betty Diamond and Kevin Tracy and some others at Feinstein have been doing some work looking at what happens when somebody survives sepsis. Because we know life expectancy is significantly shorter following a bout of sepsis in humans. And so they're looking at what happens in the brain following sepsis and how that manifests physiologically later on, and is actually shortening lifespan. So it's really fascinating work that's putting all these pieces together.
Yeah, certainly. For me, some of the kind of more clinical side of things, with regards to autoimmunity, with regards to brain function overall, mediated through that anti-inflammatory pathway through the parasympathetic side. I'm interested to find out, is there any understanding with regards to vagal tone? What would, beyond some of these challenges that occur during development, what else are we noticing throughout the lifespan of in an experimental area or in a clinical day-to-day area? Are we finding any triggers or any causes to lowering vagal tone overall?
JP, I wouldn't be surprised if you have some specific thoughts on that. The preamble I'll give, and then I'd be, again, interested to hear what JP thinks, is, I think, so people tend to, it's not the only thing, but people tend to look at heart rate variability as the indicator of vagal tone and how that might correlate with clinical outcomes. That's been done in a bunch of different indications. And, I think at the end of the day, and there are other things, but you can look at pupillary responses, you can look at skin conductance, there are lots of different things that you could do. I think at the end of the day, though, the real question becomes, for any of those measures that you might take, what does that mean in regard to the function of other organs? Like, you do heart rate variability, that's telling you about how the vagus and the sympathetic system is controlling the heart.
Yeah.
Doesn't necessarily mean it's telling you anything at all about how it's controlling the immune system or kidney function or liver function. The vagus nerve is a big bunch of fibers. Yeah. And they all have, the fibers in that nerve all have specific destinations and specific functions. And so just because you're looking at the activity in one set of fibers, feeding the heart, for example, doesn't necessarily mean that that same sort of activity is making its way to the spleen.
So I thank you for the invitation to have an opinion on this, because I do. My feeling, and we've talked about this on this podcast before, is that the body is a symphony, and to suggest that the heart could be in rest and digest mode, but that the kidneys could be in fight or flight mode, because different fibers within the vagus are firing differently, isn't impossible. But I don't view it as a stable state. I'm an engineer by training, so much like you, I look at things sort of in a mechanical system way, and so I view certain states being stable. Like, as you said, rest and digest, and we like to say rest and digest and restore or recover mode versus fight or flight. Those are two states. There's also sleep, which has interestingly, sleep has a more of a pro-inflammatory state in the brain than you would think. You think of sleep as being very anti-inflammatory, being sort of calming, but there's lots of different inflammatory cytokines that are being used to sort of prune the network and clean everything out. So it's a different state in the way it functions. There's probably different states that the body can be in, and all of the organs sort of have to participate in that in the same way. And if they're not, then I think they'll very quickly all move in that direction. I think there's some clinical cues and observations that we can state as maybe not evidence, but sort of hinting at the fact that that's the case. For example, metabolic disease. It's pretty difficult to have non-alcoholic fatty liver disease without having some other problems with your HbA1cs, and hypertension certainly goes along with that, and being overweight. I mean, those things all sort of go together, and we understand that they go together because there's a pro-inflammatory environment associated with being overweight, and being overweight then leads to the activation of sort of intracellular mechanisms for shutting down inflammation in fat and muscle cells, but it activates inflammation in the liver, and it causes gluconeogenesis to be upregulated. It causes other things to happen. It activates the sympathetics, and you end up with a higher risk of atherosclerosis. So all of those things sort of go together as a symphony. I also think you can look at conditions like fibromyalgia and chronic fatigue, where there's just a whole spectrum of different symptoms that they're experiencing, and that we find generally that if you modulate the immune system properly, even though people say, well, that there's not high levels of cytokines in fibromyalgia, or some people say there are, but some people say there aren't. But it turns out that blocking toll receptors with naloxone, low levels of that will have an effect on the immune system. That I think that all the symptoms sort of get better, or all the symptoms sort of get worse, and stress activates all those symptoms. And so I think it's true that there's different fibers that are bringing information up to the brain, but what the brain does with it, it synthesizes it. The brain is synthesizing, it's extracting meaning out of those signals from all over the body. And I just don't think you can have for very long one organ being sort of out of step with everything else. I think they all sort of go together, which is why you see such high levels of comorbidity among people who have autoimmune diseases. They have other symptoms that go along with that one index indication.
Yeah, point well taken. I like that analogy, that it's a symphony. That does make a lot of sense. I think the other thing that hampers certainly heart rate variability as an index of what's happening is the technical challenges with that. We know that it's got a diurnal pattern to it. We know it's got a seasonal pattern to it. How exactly it's measured and how the calculations are done. It's a very complicated endpoint that I don't know if it can be standardized better than it is. But I think that certainly for those of us who work in the transcutaneous space, right, trying to deliver neuromodulation therapy through the skin, having some robust biomarker of activity is kind of the holy grail for us, right? Mm-hmm. It's one thing when you wrap an electrode around a nerve and turn on the pulse generator, you're pretty confident you're stimulating that nerve. When you're trying to work through the skin, you have to start looking at these secondary endpoints that are really kind of critical to prove that your device is working the way you want it to. And I would love to see whatever it might be, pupillary responses or saccades or something, popping up as the thing that can be robustly monitored as a measure, both of neural target engagement and effective therapy application, but even of as a symptom, as an indication that things are abnormal, and that we could try to rectify them with a neuromodulation device.
So we actually have along the way discovered a couple of things, and one of them is an analog to heart rate variability called cardiac vagal tone. I don't know if you've run across cardiac vagal tone. It was developed as a sort of a mathematical algorithm for taking the heart rate variability raw data and calculating this high frequency component piece. And we found that was a very good indicator of whether or not the vagus nerve was actually being activated. So I think the company that originally developed scope and they're no longer in business, but I know that there's some people who've carried that work forward, and I know that their math can be recreated. But that was one which we actually ran a study, and we were able to show that in 100% of the subjects there was an increase in cardiac vagal tone that was statistically significant and lasted for up to 24 hours, still being statistically significant in that measurement. So cardiac vagal tone is sort of my personal favorite. The other is obviously EEGs that can be done. That's not as easy to do. I think cardiac vagal tone I think Apple Watches used to do it or still do it, and the Cardio Mobile app can get you a reading that's good enough to measure the cardiac vagal tone. So that's one that I think is something that could be used clinically. Frankly, I think a physician who wants to measure cardiac vagal tone and then see whether or not a transcutaneous stimulator is having that effect, that's very easy to do. But it's not well known. So if you didn't, that's maybe I'm actually going to be useful in this conversation. I give you a little bit of information. The other is the EEGs, and that's more difficult to do. But hopefully that technology is coming around. Obviously, fMRI will tell you whether or not your device is actually stimulating the vagus nerve, but I don't think we want to spend $5,000 to ensure that everybody's actually getting stimulated.
And I think I'm not very familiar with it at all, but I definitely have heard of cardiac vagal tone. I know that that's been an endpoint that you and others have looked at. I specifically did not mention EEG or worse, fMRI, because, again, the way I think about this, when I think about a wearable, a transcutaneous device to provide neuromodulation, I'm thinking about somebody walking around with it all the time. I'm not thinking about somebody in the hospital in an fMRI machine. And so, yes, scientifically, it's important to look at brain signaling and use fMRI to demonstrate that you're engaging that target. But the real question is, well, when somebody's walking down the street to Starbucks and that device turns on, wherever they're wearing it or however it might work, or if they're sitting on their couch and they turn the device on, are they engaging it when they're at home alone, using that thing by themselves, and having that moment-to-moment user-friendly feedback is where I think that things really need to go.
Yeah, and I know that there is a cardiac vagal tone watch that's been developed over in the UK that was sort of a follow-on, a evolutionary advance on the original neuroscope. So they're using the same algorithm. My understanding is that they're only using it and selling it for clinical studies, and it's not widely commercially available. But I think that's a miss, and maybe we'll get a groundswell of people wanting the devices and calling them. That would be a wonderful outcome of this conversation. But it would be wonderful if they were widely available, because I think you're right. Seeing somebody walking down the street towards Starbucks and their wristwatch is connected by Bluetooth to their phone, and their phone signals to them that, hey, listen, your cardiac vagal tone is lower than it should be. Might want to do something. Yeah, get the decaf, not decaffeinated. Or spend some time in Starbucks doing some deep breathing exercises or something like that. Might be a great wearable and a lifestyle fitness thing for people to do.
Mm-hmm. Agreed.
I'd love to ask a little bit more with regards to your research in rheumatoid arthritis and autoimmune conditions and the control of vagus nerve stimulation in those cases, and kind of what you've seen in the research as you've been working on that.
It's a little bit open-ended. I'm not sure where to go with that. I think what I would first preface my answer with is that, again, I'm a basic biologist, right? I'm a basic immunologist, and my work is very laboratory focused. It's very animal model focused. But my work also was not really in rheumatoid arthritis. The things that we had done, and even the lab, the Tracy lab more globally, we were really interested in sepsis. That was what we were really going after. The foray into some of the more chronic inflammatory conditions like RA or IBD came secondary to that. And Kevin has published extensively on why he was interested in sepsis. He's got at least one book out, maybe two, that describe his clinical path that led him to sepsis. What we, and it's a collective we, like many of us, realized over time is that a lot of the pathways that are involved in the pathogenesis of sepsis overlap with the pathogenesis of RA and things like that. And so, perhaps that's why I'm stumbling around a little bit for an answer to your question, because, I really thought about all of this at the level of how does the vagus nerve get a signal to a circulating monocyte or a tissue-resident macrophage to affect disease progression, right? And so that automatically reduces me. I was lucky enough that I was not in a lab that was really focused on macrophages in cell culture. We were really thinking about them in the context of the greater animal. And so, that interplay between the nervous system and the the immune system were some of the key questions that we were pursuing. So that was not an answer to your question. That was more a backdrop to how I might think about answering your question, but I might want to ask for a little bit more specificity about where you'd like me to go.
I guess more with regards to the specific pathway of control of macrophages, maybe not necessarily in the context of RA, but rather in the production of an inflammatory or in the reaction to excess inflammation. And so what kind of happens in a case of sepsis or RA or IBD, kind of as you stated, that the pathways are overlapping. What are we noticing is happening with regards to macrophage activation when there is acetylcholine present versus not present, and whether it's coming via vagus nerve or via T cell, kind of magnifying it at the splenic level or whatnot?
Okay. All right. Good. Thank you. That helps me pigeonhole it somewhere I can speak a little bit. So, what tends to happen in inflammatory reactions, is that the macrophages change their phenotype. So macrophages can have actually it's multiple different phenotypes, but generally speaking, it's in two broad buckets. And this applies actually to JP's point from a few minutes ago to microglial cells as well. So there's one generally pro-inflammatory phenotype called the M1 phenotype. And then there's, again, this is a broad bucket. There's actually subdivisions of it, but there's an M2 phenotype, which is more of an anti-inflammatory tissue regeneration sort of phenotype. And one of the key observations made by us and others is that vagus nerve stimulation or cholinergic receptor engagement tends to drive the macrophage to the M2 phenotype. So less pro-inflammatory, less of the dumping out of TNF and IL-1 and all those really pro-inflammatory cytokines that are the alarm that there's a big fire happening and all the macrophages need to come in and invade. As opposed to that shift to M2, things become more quiescent. It's more about dealing with it locally and shifting into that tissue regeneration mode, which is probably why, again, coming back to some of the things that JP talked about earlier, why there is this activity of the macrophage or the microglial cell and development and axon pruning and all of that. That's all consistent with that overall notion that macrophages have that tissue regeneration capability. And that's really what I think is at a cellular level, the important aspect of what vagus nerve stimulation is doing is it's getting macrophages to fix the problem as opposed to raising the alarm and bringing everybody in to try to deal with it.
So in the pathway, the understanding is, as I understand it, is that the vagus nerve has on it receptors for TNF alpha and IL-1 beta. And so it's one of the sensory jobs it's doing is sensing the immune system and how the immune system is functioning. But it's doing a lot more than that. The vagus nerve has hundreds of thousands of fibers. If you add up the ones on the right and the left, I think it's somewhere closer, maybe even over 300,000 fibers. Could be even more than that. And it's bringing information constantly up into the brainstem through the nucleus tractus solitarius. Is obviously acting on different centers to cause the release of neurotransmitters, but there's information that's coming up, and that information is coded in frequency and in location and other things. And that information has to be processed. We've talked on this podcast about the fact that when you close your eyes and then you open them again, the world suddenly just appears in front of you. But there's something far more complicated that's going on, and the brain is actually taking a relatively small amount of information and creating a full visual field for you that is in part in very large measure generated by expectations of what it expects to see. Mm-hmm. And so the same thing is occurring in your auditory centers and in all of the other areas of your brain that control the center, the five senses. But there's really more senses than just the five ones that we think about. There's also the sense of how our bodies are functioning. And so as information is coming up into the brainstem, you have this processing that's taking place in the brainstem of that information to produce a truly conscious sense of how you're doing. And, if you're sick, then it's going to tell you you're sick. And if you're feeling tired, it's going to tell you you're tired. And if you're feeling hungry, it's going to tell you you're hungry. If you have to go to the bathroom, it's going to tell you you have to go to the bathroom. All of those things are it's information coming up into the brain. It's not so simple as to say, oh my, the old joke with, what was the daredevil who said, oh, I think I broke my spleen. You don't get that level of detail. You don't know, okay, my spleen isn't functioning properly, but you know that you're not feeling well. And so you have this information that's coming up through your vagus nerve and through your autonomic nervous system into your brainstem, and you're getting this perception of health. And then your brain sends signals back down to your body in order to do things to perhaps help with that situation. Controls digestion, controls heart rate, but it also controls how you feel, so that you may experience symptoms. We call it the sick program. Activates a sick program if the information coming up is such that you should feel sick, then you're going to respond that way. But the microglial cells are playing such an important role in how the brain is functioning that it can't not have an effect on that perception. So for some people who are primed, we know, for example, in fibromyalgia, that some incredibly large portion of people who have fibromyalgia suffered some form of abuse or early childhood trauma. And that would suggest that their microglial cells, which have this long-term immune memory, have been primed and now function differently. And that's why drugs like low-dose naltrexone and certain other anti-inflammatory drugs like minocycline can have an effect, or milnacipran, that are having an effect, not because they're masking the symptoms, but because they're affecting the immune system in the central nervous system, so that the microglial cells will calm down into that more M2-like state. I suspect that there's something very similar happening down in the body. But the question from what you were describing that sort of hits me is, okay, in the spleen, it's been very well described. You have this release of norepinephrine, noradrenaline, depending on which side of the pond you're on, and then you have this chat cell that's tissue resident T cell. Even though it's a nascent T cell, it's there and part of the adaptive immune system, and it's releasing acetylcholine that then triggers this alpha-7 nicotinic acetylcholine pathway, blocking the whole inflammasome. In circulation, how does that work? We know in the gut it's different because there's direct innervation with the vagus, and the release of acetylcholine can be direct onto the progenitor cells that can either differentiate into Th17 or into Treg cells. But how does it work in circulation, for example, in a joint or in in the liver or somewhere else where, well, especially in circulation, how does that anti-inflammatory signal get there? Is it circulating chat cells that are just constantly releasing acetylcholine, or what is it? How do you describe it? How do you think of it?
No, I think my understanding of it is that the T cells, the chat positive T cells that are that interneuron, to use your word from before, conveying that message to the circulating cells, that's taking place in the spleen, in the pathways that we've studied. Now, again, there are lots of different things going on. There are other pathways involved here, but I'll speak specifically about the spleen. So my understanding, in large part based on the work that Mauricio Rosa-Spallina had done and published, those T cells are resident in the spleen. And what they're doing is they're releasing acetylcholine into the bloodstream. And the monocytes are picking that up. And that engagement of the nicotinic cholinergic receptor on those circulating cells, I think, though I don't have data on this, but here's my hypothesis, is that that's basically permanently changing the phenotype of those cells, so that when they are arriving at an inflamed joint, their predisposition is not to raise the alarm bells, but to go in and try to fix stuff. And I think that's happening in the brain as well. So the microglia I don't know that the half-life microglia because I'm more of a peripheral nerve immune system guy. But the monocytes, macrophages, other cells in the bloodstream, have kind of defined half-lives, and they're not very long. They're on the order of days. And I think what's happening is that you get this burst of acetylcholine release, which Mauricio has shown happens over minutes, right? You do a burst of stimulation I think he did it for 30 seconds, and he measured acetylcholine release directly into the spleen for, I think, half an hour, and it peaked around 20 minutes. So after stimulation. So it's a prolonged acetylcholine release from these interneurons, these T cells. And that the cells, as they're circulating, coming through the circulation of the spleen, are picking that up and remembering basically what the brain is telling them to do, which is to get to a site of inflammation and go in there and start fixing stuff, not to throw off alarm bells. You're not the detector anymore. You're the fixer. And I think that's how that process happens.
So in the central nervous system, there's probably a more direct path with the activation of the nucleus basilus and Maynard's and the release of acetylcholine directly from there. That's the center for acetylcholine release, and we see it's upregulated with vagus nerve stimulation. So I think there's a separate pathway there, but that's really interesting. So what you're saying is that the release of acetylcholine directly into the bloodstream through the spleen leads to the downregulation of peripheral tissue macrophages and circulating monocytes for an extended period of time.
Mm-hmm.
How do those macrophages that are now, or monocytes that are going to move into the joint, because the joint is somewhat separated from the vasculature, but there is communication. You got synoviocytes and other tissue, other cells that are in there that are actually contributing mightily to the degeneration of the bone. So you're saying that it's sort of it's a telephone chain, if you will. You got the release of acetylcholine from the chat cells that are tissue resident in the spleen. That acetylcholine is affecting peripheral monocytes. The monocytes are somehow also communicating with the synoviocytes, or is there direct innervation of the nervous system into the joint that would do this otherwise? Or is it just not known? I mean, it may not be known. I mean, I just.
Yeah, so the monocytes. So I think generally speaking, it's really not known. Joints certainly are innervated with sensory neurons. Whether there are autonomic neurons is open to question. I think I haven't really looked at that in any detail. There's very little reason to think that that parasympathetic nerves get there. So which is kind of how we came on this idea that, the education of the monocytes happens in the spleen as they're coming through the circulation, and it's changing the phenotype of those cells so that then when they do get to the inflamed joint and they migrate through the blood vessel wall into the joint and differentiate into a macrophage, that the way that they will respond to that environment is different than had they not received that cholinergic signal, right? And so had they not gotten that cholinergic signal, they'd have gotten into that joint, they'd have said, oh man, there's a fire here, let's call in all the backup and get everybody coming in here to tackle this problem. Instead, because they've gotten that, they move into this remodeling mode without exacerbating the inflammation that's there, if that makes sense.
Yeah, no, it does make sense. I'm just wondering whether there's any, are there any of these chat cells either in circulation or potentially in the joint? I mean, when I think of bone, I sort of grew up in the orthopedic space in the medical field. And so osteoblasts and osteoclasts, but osteoclasts are a macrophage. They're a form of macrophage. And so, is it possible that the bone and the joint degeneration that's occurring is a result of that macrophage being in play? And that are there tissue resident T cells, those chat cells, that exist in the joint so that sympathetic innervation could actually activate them, and that the reflex, and I'm completely speculating here. I mean, we're this blue sky moment here. Is it possible that we have you know, chat cells and the tissue resident macrophages, which are the osteoclasts, which are designed to break down bone, are present and are being activated. And that, you know, I guess a way to test this would be in an animal model of rheumatoid arthritis, where you remove the chat cells, but then give a cholinergic signal, like inject acetylcholine. You know, would you then see that degeneration abate, or would you see it not be affected because that's not where the source of, or, you know, how that model would work?
Yeah, it's an interesting notion. I'm unaware of anybody that's looked for distribution of those chat positive T cells. Not saying it hasn't been done. It's not something I've watched that closely. But you know, so I don't know. I suppose it is entirely plausible, and in fact, it's probably hard to imagine that chat positive T cells would have evolved and not found a way to be useful elsewhere besides the spleen. So it's a great hypothesis as far as I know. I haven't seen data that speaks to that, to me, it's a really interesting question.
Well, I guess that's for the future broadcast when somebody's actually done that work.
Absolutely. One last question I think would be really a good one to end on. And JP, I think you had alluded to this earlier, just off the recording or previous to us starting the recording. But question with regards to what the Australian group kind of was understanding to be kind of their hypothesis, more on the sympathetic activation or sympathetic control of inflammation versus the parasympathetic side. Did you want to lead into that?
Yeah, I mean, just the group out of Australia that has written a number of papers, I see that they've sort of walked back their original criticism. Their original criticism was quite robust. They said, no, this doesn't work. It's not true. It's all done by the sympathetics. And they've walked that back. And I think in their most recent paper that I've seen, I think it was from a year ago. So maybe they've even further refined their thinking. But they said, no, we get it. This works. But it's really something akin to a biohack. That's not the way Mother Nature really does it, and that you can activate this through the sympathetics. And the reason why it's interesting to me, and is that there is some work that's been shown that if you directly stimulate the splenic nerve, you can get this, which is a sympathetic nerve. You can get this same effect, and that the same anti-inflammatory benefit, because again, you're looking for the splenic nerve to release norepinephrine, the chat cells to release acetylcholine to activate this process. You don't really need that splenic nerve to be activated by the vagus. You can have it be activated through the greater splenic nerve, which is again part of the sympathetic pathway into the spleen. So I'm just wondering whether or not, you know, that they're not wrong that you can activate this pathway through the sympathetics. But is it really the way Mother Nature does it? And the reason why I think not, I don't want to put words in your mouth, but the reason I think it's not is that the sympathetics, and Dr. Habib and I have talked about this on prior podcasts, the sympathetics really drive you away from homeostasis. That releases norepinephrine. There's two different types of beta receptors, beta 1 and beta 2 receptors. And if you activate beta 1 receptors, it's pro-inflammatory. If you activate beta 2 receptors, it's anti-inflammatory. So it's not surprising that the sympathetics could do that, but I would think it's confounded. I don't think it's clean. The parasympathetic seems to be a much cleaner pathway. And again, not putting words in your mouth, but I'd love to hear your thoughts about their theories and then maybe some of the blah, blah, blah that I just said.
You know, I think that I think what has become clear over probably the past decade is that there are indeed multiple things happening here, right? So the HPA axis is involved, the gut is involved, like all kinds of things are happening here. And I don't think that any one particular pathway is the be all end all. And on top of that, I would say, maybe more importantly, there is a distinction between what Mother Nature's doing and what kind of biohacking we can do to provide therapy. And I'm more interested in the latter than the former. I mean, yes, the former is important. Obviously, you can't do the latter without knowing the former. But on the other hand, if we know we can obtain therapeutic benefit by stimulating any particular process, just to even take it out of neuromodulation, right? If there's a particular process that we can modulate and control and have therapeutic benefit, I don't necessarily find my mind wandering back to, well, what does Mother Nature do? I'm more interested in how can we optimize that therapy, right? How can we make it better? But the reality is there are multiple pathways involved. And I do think that there is evidence that the splenic pathway and the acetylcholine pathway are critical. I mean, I use that in a very broad sense because I didn't do a lot of this work. But at the Feinstein, my colleagues did work where, knocking out the alpha-7 receptor and showing what happens downstream when that receptor is not there. Doing various neurectomies, like actually cutting nerves and blocking effects, and putting into the system antagonists of the receptors, like all kinds of different things have been done to explore and to show that in the absence of the pathway. And I mean, I think Ludmilla even did this in her very first paper in Nature. Removing the pathway hypersensitizes animals to an inflammatory insult. And so I don't doubt that so that's in the absence of electrical stimulation. Like you knock out alpha-7, for example, and animals more sensitive to an inflammatory stimulus. So I think for sure there's a Mother Nature story in there, that there's a normal biologic process in there. Whether we are hyperactivating it or biohacking it in some way when we apply stimulation, yeah, that could very well be. There could be an element of that. And I'm not a fan of digging my heels in and saying that the cholinergic anti-inflammatory pathway, or the term we haven't used here but is probably even more appropriate, the inflammatory reflex, is the one and only thing that does all of this. That's kind of crazy. I don't buy into that. I think all of these things are happening simultaneously. And, to your point, JP, it's a symphony. And it'd be crazy to think that there's one and only one pathway through which this can happen. It wouldn't make evolutionary sense to have just one pathway. There's got to be multiple. But again, where I come back to it is if we can achieve the therapeutic benefit without side effects, then we're on the right path. And if it's a biohack, it's a biohack. I don't. Maybe that's a badge of honor as opposed to a criticism.
Well, as an engineer, I agree with you. That if you figured out a way to hack the system, that's even better than just tagging on to something that was naturally there. But I tend to agree with you that Mother Nature loves, as you said before, Mother Nature loves to repeat herself. If she's found a good way of doing something, she's going to reuse it over and over again. And so I think that's something going on. I also think, and we've talked about this before on the podcast, that inflammation is and the immune response to inflammation or into challenges can be so robust it can kill you. And so as a result, there really have to be redundant systems. As an engineer, you love redundant systems, a safety factor. And so, yes, there may be other pathways that work and other ways of activating not only this pathway, but other pathways like the HPA axis and glucocorticoids, and then the intracellular pathways of the SOX proteins and things like that. They're all there basically because the immune system is so powerful that it can kill you in a matter of seconds. And so there really have to be control mechanisms for it. The vagus nerve does appear to be one that's very rapid. You pointed out that the effect can be had in some of the models that you guys have looked at in 30 seconds. I've read one paper that says even one single pulse can activate, which would last a 30th of a second, can affect the system in a positive anti-inflammatory way. we've seen in some of the work that we've done in animals that, even if you mistakenly transcutaneously stimulate an animal for 3 seconds, it has the same benefit in certain models. Other ones other ones it might even take 2 or 3 different stimulation periods. But in stroke, we've seen similar things, and in headache models, we've seen it. So I think you're right that the system can be triggered very quickly. Mm-hmm. It's probably used in multiple places, in multiple, and we're finding them in the gut and in the brain and in the spleen. I think we're going to find ultimately that there's dozens of different pathways that are mirrors of it. And I think that ultimately Mother Nature needs many ways of managing the immune system, because if not, the system can get out of hand. And so inflammation does appear to be at the root of so many different clinical problems that I think it shows how, in my mind, the innate immune system and macrophages are at the heart of who we are, and they control our lives in ways that we can never really truly appreciate, because we think of ourselves as being, defined by our internet and our jet travel and our nice restaurants and things like that. But at the end of the day, 99.9% of what actually affects us in our lives is happening at the subconscious level. And the immune system and the central nervous system are working hand in glove, hand in hand, doing everything for us. So getting that in the right place is something we need to do. And this is a great, whether it's a biohack or Mother Nature's way of doing it, it's a great way to center yourself. It's a great way to get back into rest and digest and restore mode. So we're big fans of all the different ways of doing it, whether it's Gregorian chants and dancing, or gargling cold water and prana breathing techniques, or going for a run, or stimulating using electricity, or anything. All of it works, and all of it's really, really good.
Agreed.
I love this. This was an amazing conversation. Had a lot of fun listening to the two of you banter. I love this engineer researcher talk going on around me, and me chiming in with my fun little clinician stuff here and there. But this was wonderful, and I really do appreciate both of you coming on. Dr. Czura, it was absolutely an honor and a pleasure to have you on, and thank you. We'll definitely have you on again, as I know you are expanding where you're looking into, and some of the amazing work you're doing with regards to platelets and blood and kind of the bleeding mechanisms that you're learning about as well with regards to vagus nerve stimulation. So we'll definitely have you on when there's new research to be discussed at that point. But this was a wonderful episode, and we're excited to share this with all of you. So just as always, if you appreciated what you heard here, what you learned, what you heard, and want to share with somebody, please do share this with anybody that you think needs to hear this, whether it's a clinician, a friend, a family member, whoever can use this information to the benefit of their health. Thank you guys so much for listening, and we'll see you on the next episode of the Health Upgrade Podcast.
It's a pleasure to be with you. Thank you very much.
Thank you.